today we'll be looking at electrolysis calculations. Now, all those gases that you saw coming off at the anode or the cathode, we will be able to calculate their volumes, or certain masses that came off at the cathode, or if a mass came off at the anode, you can now calculate that mass of substance that is produced. Let us look at the objectives that will be covered in this topic. The objectives are: 1, we're going to state Faraday's laws, and of course the calculations are based on Faraday's laws. We're going to define the Faraday's constant, and then we're going to carry out our calculations involving masses and volumes of substances liberated during electrolysis. Let us begin. Let's look at Faraday's laws. The first law is saying that the mass of a substance liberated during electrolysis is directly proportional to the quantity of electricity used. So this part here is very important. Directly proportional to the quantity of electricity passed or used. It means that the longer you run the current for, the more mass will be deposited at the cathode. Or the longer you run the current for, the more or the greater the volume of the gas will be. So this is very important. Faraday's first law. And it's simply saying that mass, and I should say or volumes, liberated during electrolysis is directly proportional to the quantity of electricity used. From that, we can find out the charge, and the charge here would be Q equal IT. So we can work out the charge using I times T, where I is current and T is time. The second law is saying that for 1 mole of various atoms, 1 or more moles of electrons can be liberated. So if you have 1 mole of, say, silver, we know that silver would produce only 1 mole of electron. We can have 1 mole of aluminum, and that will produce 3 moles of electrons. Let us look at it a little more. Bear in mind that all the calculations will be based on Faraday's 2 laws. So the amount of electricity in coulombs required to produce 1 mole of a substance is a multiple of 96500. That's 96,500. And this is Faraday's constant. So from that, you can get that 1 Faraday is equal to 96500 coulombs. So the Faraday constant, F, is the quantity of charge on 1 mole of a substance. So therefore, 1 mole of a substance will have that charge of 96,500. If the charge is 2, then that would mean that 2 times Faraday, which is 96500 times 2. So here we have now 1 mole of a substance. In this case, it is 1 mole of hydrogen ion. And that would liberate 1 mole of electron, which means that if it liberates 1 mole of electron, then the charge is 96500. So it is very important to know and write the half equations. So for H plus, we have 1 mole of electron being liberated. So you'll see that 1 mole of electron being liberated, it will be 96500 coulombs. Now, if you write the half equation, you'll notice that in my half equation here, I now have 2 moles of electrons liberated. Hence, that would be 96500 times 2. For copper, we have 2 moles being liberated to form copper atom. Again, this would be 96500 times 2. Because 1 mole of a substance will liberate 96500 per coulomb or per charge. So per charge here, it will be 2 for copper 2 plus and 2 for H plus. For 2H plus, it will be plus 2. Hence, 2 times 96500 coulombs. 1 mole of a substance in case of aluminum ion, that would liberate 3 moles of electrons to form aluminum. Hence, per charge, it will be 96500 times 3. So when you write your half equations, look for the number of electrons that are liberated, and you will multiply Faraday's constant by that number of electrons that is liberated per mole of substance. Let's talk a little more about the charge. Now, according to Faraday's first law, we can work out the mass deposited at the anode or cathode, or volumes deposited or discharged at the cathode or anode, depending on the quantity of electricity used. And the formula we use is Q equal IT. Now, Q is the quantity of electricity or the charge in coulombs. Current, I, is in amperes, and T, time, is in seconds. So if you get Q equal IT, and we say that Q is in coulombs, and I is in amperes, and time is in seconds, then you can see that 1 coulomb is equal to 1 ampere second. So another unit for coulomb is really ampere second, as you can see here. Now if Q equal IT, we can always transpose to get current. So if we know the charge and we know the time, we can find the current by transposing, making I the subject of the formula. So I would be equal to Q over T, shown here. And if we get Q equal IT, and we know the charge and the current, we can find time. Where time is our unknown, we would transpose to get time. Therefore, time would be equal to Q over I. And of course, from our original equation here, Q equal IT, if we know the current and the time, we can calculate the charge in coulombs. Let us look at some examples of how to apply this formula Q equal IT. So let's start by looking at this example. We are to calculate the quantity of electricity Q obtained when a current of 25 amperes runs for 1 minute. Now remember, the longer we run our current, the more substance will be deposited. In other words, the higher the charge or the quantity of electricity, the more mass will be deposited, or the greater the volume will be produced or liberated at the anode or the cathode. So from this question, we must look at the important terms. What do we want and what do we have? Well, we want to calculate Q. So in this case, Q is our unknown here. What do we have? We have the current and we have the time. So we have current and we have time. Now, in terms of current, we know it must be in amperes and time must be in seconds. But you'll notice here that our time is in minutes. So what do we need to know? We need to know that 60 seconds is equal to 1 minute. And so, in this case, since I have 1 minute, it is really 60 seconds. So from our formula, Q equal IT, we can put in the information we have and do our calculation. So we have 25 amperes, that's our current. And so Q is equal to 25 amperes times 60 seconds. And so when you multiply 25 amperes by 60 seconds, you get 1,500 ampere second, which I showed you is the same thing as coulombs. So this is the calculation for finding Q given current and time. Let us look at some other examples. In this example, we are to calculate the current. So this time we want the current needed to provide 30,000 coulombs, that's Q, of electricity in 5 minutes. So what current or what quantity of current must I provide in order to produce 30,000 coulombs of electricity in 5 minutes? So what do we have? We have Q, we have time. Again, time in minutes must be converted to seconds, and we want to find current. So if we know that Q equal IT, we know that we have Q, we have time, we need to find I, then I is equal to Q divided by T. And in this case, we know that Q is 30,000 coulombs over time, which is 5 times 60 to convert from minutes to seconds. And that is 300 seconds. And so in calculating 30,000 divided by 300, we get 100 coulombs per second. And you should know that 1 ampere is the same thing as 1 coulomb per second. So our current here is equal to 100 amperes. And this is our answer. So we simply rearrange our formula Q equal IT to calculate the unknown. Let's look at some others. So you saw in the first example that Q was our unknown. You saw in the second example that current was our unknown. Now our unknown is time. So what time do we require to produce 12,000 coulombs of current using a current of 10 amperes? So calculate the time required to produce 12,000 coulombs of electricity using a current of 10 amperes. So we know that we know the current, we know the quantity or the charge, we don't know the time. So again, starting from our main equation, Q equal IT, we know Q, we know I, we need to find T, so we make T the subject of the formula. So T is equal to Q over I. Q is 12,000 coulombs and I is 10 amperes. So you can see here that in dividing 12,000 by 10, our calculation would give us 1,200 seconds. So the time that is required is 1,200 seconds to produce 12,000 coulombs of electricity using a current of 10 amperes. Now you could convert back your time into minutes if so desire by simply dividing by 60. And so if you want to convert your time from seconds to minutes, then that would now be 20 minutes. Now we know how to use Q equal IT to find Q, I, or T. We are now going to use Q equal IT in calculating masses or volumes. In carrying out this calculation, we are going to use the proportion method. It is very simple to use the proportion method when doing electrolysis calculations. Remember, you must know your half equations, because if you don't know your half equations, you won't know the number of electrons liberated. So you need this number, so we need to know how much must we multiply Faraday's constant by. Let's look at this problem. The first thing we must do is to calculate the quantity required to find out the mass deposited. So in this case, we're going to start with Q equal IT. So we know that I is in ampere, so it's 1.0 times 10 to the 4 times time, which is 24 hours. But remember, we must convert from hours to minutes to seconds. So that is why you see I multiply 24 by 60, which will give me minutes, then by another 60, which will give me seconds. So there are 60 seconds in 1 minute, and there are 60 minutes in 1 hour. And so we can carry out this calculation here. So 24 times 60 times 60, that is 86,400. Now I'm going to multiply this 86,400 seconds by my current of 1.0 times 10 to the 4 amperes. So 1.0 exponential, which means times 10 raised to some power. In this case, it is 4 times 86,400 seconds. And that would give me 864 million. And this 864 million will be written in standard form. So that would be 8.64 times 10 to the 8th. And that is our charge or quantity of current that is required. Now remember now that we have our half equation and we want to find the mass of copper deposited. So in calculating that mass, we're going to use the mass of 1 mole of copper. So let us say the mass of 1 mole of copper is 64 grams. So we'll say 64 grams of copper require 96500 times 2. And it must be times 2 because we have 2 electrons being liberated from 1 mole of copper ion. So that's times 2. Now, what mass of copper will be produced if we have a charge or quantity of electricity being 8.64 times 10 to the 8th coulombs? After which we are going to cross multiply. Now this 2 times 96500 is 193000 coulombs. So let us say, let's work it out step by step here. So X times 96500 times 2 coulombs and X grams is equal to 64 grams times 8.64 times 10 to the 8th coulombs. So now I'm going to multiply 2 by 96,500. So it's X times 193. 123 coulombs equal And let's multiply out this part here. So that would be 64 grams times 8.64 times 10 to the 8th. And that would give me and we're going to write our answers to 2 decimal places. So it's 5.53 times 10 to the 10. 5.53 times 10 to the 10. And this now is our calculation for this section here. Now let's divide. So it's 5.53 times 10 to the 10th. And let's put back our units here. We had grams and we had coulombs. And that is now divided by 193,000 coulombs. So coulomb would cancel coulomb there. So our answer is in grams. So let's divide now through. So now let's divide 5.53 times 10 to the 10 by 193,000. So that's 5.53 exponential 10 divided by 193,000. And that would give us a value of 286,528.50. Let's write it to 2 decimal places. So our value is 286,528.50 grams. So in 24 hours, when my current of 1.0 times 10 to the 4 run for that time, I will produce a mass of 286,528.50 grams of copper. Let's look at some others. Now in this example, it is asking that if you want to produce chlorine from molten sodium chloride, what mass would be produced if you use a current of 1 ampere for 5 minutes? So this one, again, we must first work out our quantity. So Q equal IT. And our current is 1 ampere, and we are running it for 5 minutes. But remember that we must convert minutes to seconds. So it is 1 ampere times 5 times 60. And this here would now be in seconds. So 5 times 60 is 300 times 1, which is 300. So 300 coulombs is our quantity of electricity. Now we need to understand that our molten electrolyte, what we want is chlorine. So from that, we know that Cl minus will be oxidized to form Cl2. So we must add electrons here. And we know this already from our experience with electrolysis of various substances. So right away, we realize that 2 moles of electrons are liberated. So from these 2 moles of electrons liberated, we can now calculate the mass. Now, chlorine is diatomic, and the molar mass of chlorine is 35.5. Therefore, being diatomic, chlorine being Cl2 now, that mass would now be 71. So in order to find the mass produced, 71 grams of chlorine would produce 96500 times 2 coulombs. So what mass of chlorine will be produced from a charge of 300 coulombs. So again, we will cross multiply. When we cross multiply, we will see that X grams of chlorine will be multiplied by 96500 coulombs times 2, which is 193,000. And that would be equal to 71 grams times 300 coulombs. Therefore, X grams is equal to 71 grams times 300 coulombs divided by 193,000 coulombs. So coulomb will cancel coulomb. So your answer is in grams. So let's calculate 71 grams times 300 coulombs divided by 193,000 coulomb. So here we have 71 times 300, which is equal to 21,300. And that will now be divided by 193,000. And that is equal to 0.11 grams of chlorine. So in this case, we know that chlorine is a gas, but the question wants to find the mass of chlorine. So 0.11 grams of chlorine would be produced if we run a current of 1 ampere for 5 minutes. So we're trying to look at different ways the questions can come. So let us look at some others. Now in this example, you want to plate 5 grams of silver from a solution of silver plus ion. What current would you require to run for 1,000 seconds? Now this is a bit different from the ones you saw before. So let's observe. What do we want? Well, we cannot start with Q equal IT, because you'll notice that we want to find the current I. So what current would you require to run for 1,000 seconds? So all we know in this case is a time, but we don't have current and we don't have the charge Q. So we have two unknowns in our Q equal IT, so we cannot start with this formula. So we will start by calculating Q from the 5 grams of silver given in the question. Now the mass of 1 mole of silver is 108 grams per mole, or 108 grams, since it is the mass of 1 mole. So let us start by saying now 108 grams of silver will produce 96500 coulombs. Now notice it is silver plus. If it is silver plus, it means that silver would liberate only 1 mole of electron to form silver atom. So there is no need to multiply this value by 2 or 3 and so on. Now we have 5 grams. So if 108 grams produce 1 Faraday, which is 96500 coulombs, how many coulombs would be produced if 5 grams of silver was used? Or how many coulombs would you need to produce 5 grams of silver? So now we can find Q this way from the mass of silver given. Again, we are going to cross multiply. So from that, we can now say 108 grams times X coulomb is equal to 5 grams times 96500 coulombs. So X in coulombs is equal to 5 times 96500 coulombs divided by 108 grams. So grams would cancel grams. So our answer will be in coulombs. So 5 times 96500 coulombs is equal to 482,500. And that will be divided by 108. That would give us a value of 4,467.60. So that is 4,467.60 coulombs. Now we are not through with the question because we want to know the current required. Now we now have Q and we have time. So let's find I. So from that, Q equal I T. And since we have Q and T, we can find I. So I is equal to Q over T, which is now 4,467.60 divided by the time of 1,000 seconds. And so divided by 1,000, 1, 2, 3, our answer will be 4.50 amperes. So a current of 4.50 amperes would be required to run for 1,000 seconds if we want to plate 5 grams of silver from a solution of silver plus iron. Let's continue. In this example, we want to find the time it would require to run a current of 0.5 amperes to plate out 10 grams of gold from an Au3+ solution. So right away, we realize that we would need 3 moles of electrons. So we need to multiply 3 by 96500 coulombs. What is the mass of 1 mole of gold? So the mass of 1 mole of gold would be 197 grams. So that would now produce 96500 times 3 coulombs, because we have 3 moles of electrons liberated here. Now, how much coulombs would we now need to produce 10 grams of gold? So that 10 grams would come here of gold, and our unknown is coulombs here. So we can calculate Q, then we can find T. So in calculating that, that will be 197 grams times X coulombs is equal to 10 times 96500 times 3. That's coulombs. So let's calculate this section here. So we'd have 197 grams times X coulomb is equal to 96500 coulombs times 3, which is equal to 289,500 times 10. And that would now give us this value here. Now we need to divide this value by 197. Therefore, 289,500. Remember our units here? We had grams and we had coulombs. And we would divide that now by 197 grams. So grams would cancel gram. And so our answer would be X coulomb here. So that value divided by 197 would be equal to 1469.5.43 coulombs. So this is the Q we are interested in now. So from Q equal IT, we want to find time because we know A and we now know Q. So T is equal to Q over I. So it's 1469.5.43 divided by a current of 0.5. So the time it would require is equal to this value divided by 0.5. And that would give us a time of 29,390. So our time of 29,390 seconds would be required if we are to run a current of 0.5 amperes to plate out 10 grams of gold from an AU 3+ solution. Let's look at some more examples. I hope by now you are getting the idea that anytime you are to use the quantity of electricity, you must know the number of electrons liberated. And notice we always use the mass of 1 mole of the substance. Let's continue. Now in this example, it is saying here that an electric current of 5 amperes was passed through anhydrous calcium chloride. Very important. This word, anhydrous, means without water. So calcium chloride would contain only the ions Ca2+ and Cl-. Because it is anhydrous, therefore no H+ or OH- ions would be present. So in this case, looking at this problem, we want to find out the mass of each product liberated at the anode as well as the cathode. So let's look at what's going on at the anode first. So at the anode, we know that the negative ion would migrate towards a positive electrode. Therefore, Cl- would be oxidized. So this would be the equation going on at the anode. So this would be the equation that takes place at the anode. At the cathode, Ca2+ being positive would migrate towards the negative electrode. And so calcium ion would be reduced. Now that we understand what is coming off at the anode and the cathode, we can now calculate the masses. Before we calculate the mass, we need to have an understanding of what is our Q, what is the quantity of current that is passed. Now, if you look at your problem here, we have the current and we have the time. So we can work out Q. So Q equal IT. So the current is 5 times the time of 20 minutes. So it's 20 times 60. So Q would be 20 times 60. That is converting minutes to seconds. And that would be equal to 1,200. And that we will now multiply by 5. And that will give us a quantity of electricity of 6,000 coulombs. So we know Q now to be 6,000. Let's go ahead now and work out the mass of chlorine deposited at the anode than the mass of calcium deposited at the cathode. So for chlorine, we know it's Cl2, so the molar mass would be 71, and we know that 2 moles of electrons were liberated. So that would be 71 grams of Cl2 produces 96500 times 2 coulombs. Let us separate the calculation here. And X grams of chlorine would be produced by 6,000 coulomb. So how much? What's the mass that will be produced by 6,000 coulombs? Now we're going to cross multiply. So from that, X is equal to 71 grams times 6,000 coulombs divided by 193,000 coulombs. So our answer here will be 71 times 6,000 divided by 193,000 coulombs. So 71 times 6,000 would be equal to 426,000. And that now we will divide by 193,000. And that will give us a mass of 2.21 grams. So a mass of 2.21 grams of Cl2 would be deposited or liberated at the anode. Let's check to see what mass of calcium would be liberated or deposited at the cathode. Same principle. The molar mass of calcium is 40 grams per mole. So 40 grams of calcium would be produced from 96500 times 2 coulombs, since 2 moles of electrons were liberated. So what mass of calcium would be formed if 6,000 coulombs of electricity was run or was used? So again, we will cross multiply. So X is equal to 40 grams times 6,000 coulombs divided by 193,000. Coulombs will cancel coulomb. And now our mass here would be equal to 40 times 6,000 divided by 193,000. So 40 grams times 6,000 is equal to 240,000 here. And that now we will divide by 193,000 there. And that will give us a value of 1.24 grams. So 1.24 grams of calcium was deposited at the cathode. And so we can now write, so the mass of chlorine liberated would be 2.21 grams, and the mass of calcium deposited would be 1.24 grams. I said liberated for the gas because it has been produced and given off into the air, while the calcium metal will be produced and found on the cathode. So this is the calculation for this problem. Finally, let's look at calculating two gases liberated from a dilute acid. Now, in this final example, we are to state the names and calculate the volumes of gases formed at the cathode and anode at STP when 0.250 ampere of current is passed for 4 hours through a solution of dilute sulfuric acid. So right away, we need to see that the ions present in dilute sulfuric acid will be H plus and OH minus. We also have SO4 2 minus, but remember that OH minus is lower in the series, in the electrochemical series. Therefore, OH will be liberated at the anode, while H plus will be liberated at the cathode. So we are not going to be looking at SO4 2 minus because it is not liberated any at all. Now, since we have current and time, we can go ahead and work out Q. So the first action here is to work out Q. So Q equal IT, and I is 0.0250 amperes, and that is multiplied by a time of 4 hours, which we would convert to minutes and then seconds. So in this calculation here, we are going to multiply 4 times 60 times 60, and this is seconds here, times our current of 0.025 amperes. So let's say 4 times 60 times 60 is equal to 14,400. And now we'll multiply this value by 0.025. That will give us 360 coulombs. Now, we're going to use this value to work out the volume of gas produced. Now, notice that we have STP here, which is standard temperature and pressure. Now, 22.4 is the volume produced per mole. So instead of saying the mass of 1 mole or 1 mole, we're going to use the volume of 1 mole. So the volume of 1 mole would be 22.4. So let's do the reactions at the anode, then we'll do the cathode. So at the anode, we know that OH minus would migrate and be liberated in the form of 4 OH minus to produce 2H2O plus O2. And we'll add our 4 electrons here. And the 4 electrons here, they are very important. Let's work out the volume produced for 360 coulombs using the molar volume, which is 22.4 dm cube per mole. So 22.4 dm cube of O2, since O2 is a gas liberated at the anode, will be 96500 times 4 coulombs there. So what volume of O2 would be produced if we have a quantity of 360 coulombs here? So let's check. So again, if we cross multiply, we will get X is equal to 22.4 times 360, and that now is divided by 96500 times 4. And therefore, this is equal to 22.4 times 360. That is equal to 8,064. So 8,064 would be the value, and we're going to divide that value by 96500 times 4. So 96500 times 4 is equal to 386,000. So what is the volume then in dm cube produced here. So we are now going to divide now 8064 by 386000, and that will give us our volume in dm cube. Notice here that this would be dm cube times coulombs divided by coulombs. So our unit must be in dm cube here. So right away, we can get our unit in dm cube when we divide through. Now, 8064 divided by 386000. This would give me a value of 0.02 dm cube. Now, let's look at the reaction taking place at the cathode. So at the cathode, we know that H plus will migrate, hence H2 gas will be produced. Now remember that we said if two gases are being produced, the number of electrons lost must be equal to the number of electrons gained. So let's do that here, since we are producing oxygen and hydrogen gas. So I will now say 4H plus 4 electrons, and that will now give me 2H2 gas. Now once I have this, what is it saying to me now is that I would go ahead and say 22.4 dm cube of H2 would be found in 96500 times 4 coulombs, since 4 moles of electrons were liberated. Therefore, what's the volume that will be present in H2 if the number of coulombs is 360 coulombs here? Now, as you can see, the same calculation here would be the same calculation here for H2, because the molar volume is the same, the number of electrons liberated would be the same, and the number of coulombs would be the same. But there's only one difference. So here, if we calculate X should be equal to 0.02 dm cube, which is what we got for oxygen. Now, this is where the important point comes in. This part here, where you have oxygen here, and this part here where we have hydrogen, it is saying that 1 volume of oxygen is produced to 2 volumes of hydrogen. So if 1 volume of oxygen is 0.02 dm cube, then the volume of hydrogen must be 2 times that volume, which is 0.04 dm cubes. So if you carry out this experiment, you should observe a greater volume of gas being produced at the cathode than at the anode. And the reason for that is because 1 volume of O2 is produced to every 2 volumes of hydrogen. So you must have more effervescence at the cathode than at the anode. This concludes our lesson in electrolysis and calculations involving Faraday's laws.